Okay, there are three types of equations that we're going to need to solve that either directly or indirectly involve logarithms. So I will probably attach some rules to these, but basically one of those types is when some of the terms are logarithms. So in other words, we have a logarithmic term here, a logarithmic term here, and a non-logarithmic term there. That 2 is not part of the argument. The left side is just log base 3 of x. So the steps for these is we want to isolate the logarithms. We want to get those on both sides of the equation. So I think that I will leave on the left side log base 3 of x, add across, or add to both sides log base 3 of x minus 8, and then add 2 to the other side. So all of our log terms are on one side. And then we can use one of our properties of logarithms to smash these two guys together into a single logarithmic term. And since log base 3 of x and log base 3 of x minus 8 are exponents that turn 3's into x's and x minus 8's, we're adding exponents. And when do we add exponents typically? We add exponents when we have common bases and a product. For instance, x squared times x to the third is x to the fifth, which tips me off that my rule here is I can make this a single logarithmic expression, log base 3, of the product of x times x minus 8. And that would equal 2. And then definition log. Well, if you've been following along on logarithms with me, I just repeatedly say, for definition log, what is a logarithm? This is the exponent that would turn 3 into x times x minus 8. But since this wants to be that exponent and this is equal to 2, I can put 2 right here, which means 3 squared equals x times x minus 8. That's what I mean when I say definition of log. So this becomes 9 equals, I think I'll go ahead and distribute this, x squared minus 8x, or 0 equals x squared minus 8x minus 9, at which time I could go to quadratic formula. However, I believe I can factor this guy, and I get x minus 9 times x plus 1 equals 0. Therefore, x would like to be 9 and negative 1. Now, the problem is logarithms have some domain restrictions. The argument on our logarithm up here, these guys, this x and x minus 8, they have to be bigger than 0. I can't turn 3, using an exponent, I can't turn 3 into a number that's 0 or less. So therefore, x has to be bigger than 0 here, and here x has to be bigger than 8. Otherwise, I've got issues here. So I would suggest this. Anytime on a logarithmic expression or logarithmic equation you get more than one solution, you better be really, really concerned about that, because logarithms, the graph of logarithms, provided they're linear arguments, those are one-to-one. So be really, really concerned about what you basically, you have to always check your solutions to make sure they don't violate domains. And clearly, x cannot be negative 1. But putting a 9 in here and putting a 9 in here, that works out just fine. So final solution, x is just 9. 2 solutions should be a red flag. It can happen. It's not going to happen with linear arguments, however. Okay, so there is some logs. So to review that, we isolate the logs, group them on one side, smash them together, use definition log, proceed that way, check solution. So what makes this a sum log equation? We have a non-logarithmic term here. Okay, let's take a look at a second type of equation. Here we have all log terms. Every term in here is log, same base, same base, same base. So we could group all of those if we wanted to, but we don't have to. We can go ahead and just smash them together on the left, smash them together on the right. So this would be, when do we, since we have an exponent minus an exponent here, that's what logarithms are, when do we subtract exponents? We subtract exponents in situations like this, in quotients. So as we smash this, this becomes a quotient. ln x plus 5 on x minus 2 equals ln x. So there is smash. Smash them together on the left. There was nothing to smash on the right. But had there been another, I shouldn't put the 5 there. Had there been another logarithmic term over here, then I would have smashed these guys together. Okay. At that point, I can drop the logs. And what allows me to do that is that logarithms are one-to-one. So at that point, I can just get the equation x plus 5 on x minus 2 equals x. So am I just dividing away log on both sides? No, I'm just basically taking, just undoing the log, inverse function log on that. So at that point, we're straight algebra. I'm going to go ahead and cross multiply. I get x squared minus 2x equals x plus 5. So again, I get a quadratic. That is x squared minus 3x minus 5 equals 0, which does not factor. So maybe we have a solution, maybe two solutions, maybe no solution. I'm going quadratic. Opposite of b, plus or minus b squared, that's 9, minus 4 times 1 times negative 5, that becomes plus 20, all on 2a, 2. So that is 3 plus or minus root 29, all on 2. Those are possible solutions. Now, square root of 29 is just a little bit more than 5. So let's consider that. If I have 3 plus a little bit more than 5, that's a little bit more than 8 on 2. I'm a little bit more than 4. And if I have 3 minus a little bit more than 5, that's a little bit less than negative 2. That's a little, when I divide by 2, that's a little bit less than negative 1. So it's a little bit less than negative 1. Let's go ahead and consider our domain. For our domain, x has to be greater than negative 5 here, and x has to be greater than 2 here, and x has to be greater than 0 there, so it appears that x better be greater than 2. Therefore, this minus is not going to work, so our solution is 3 plus root 29 on 2. That number being, I'm claiming, greater than 4 fits. Okay, so second type of logarithmic function, we have all logarithmic terms, and again, those have to be the same base. So in that case, we don't need to isolate anything. We don't really need any algebra. We just start smashing things together on both sides. Once everything's smashed together and I have ln something or log something on the right, log something on the left, I can drop the log terms. Again, you must check your solutions. You should probably always expect you should expect the very, very real possibility of a domain violation. In this case, a number less than negative 1 would not work here or here. Okay, the last type of logarithmic equation. Wait a minute, you're saying this is logarithmic equation. There's no logarithm involved. Nope, but when we have a variable in an exponent, logarithms are really, really helpful for getting that variable out of the exponent. So the first thing we want to do, and this is going to take me a couple of steps, is we want to go ahead and divide and isolate the exponential term. So I want to get e to the 6x alone. So what do I need to do for that? Let's go ahead and I think I'm going to make this 7 on 1. I'm going to cross multiply here, and I get 119 equals, I think I'm not going to distribute this, 7 times e to the 6x minus 14. If I want to get e to the 6x alone, I could go ahead and start this by dividing both sides by 7. And it's wonderful that 7 does go into 119. 7 goes into 119 17 times equals e to the 6x minus 14. So I'll continue that over here to the left. I get 31 equals e to the 6x. So I've now isolated my exponential term. It's just plain old the base e to the 6x. If there was a 2 in front of the e, I'd divide both sides by 2 before this next step. So there's my isolated exponential term, step A. Step B, next, I want to log both sides. I want to take logarithm of both sides and pull exponents out. So in this case, I would choose ln because we're dealing with a base e. So I'm going to take ln of both sides. What is ln of 31? I don't know. But what does this allow me to do? I get ln 31 equals 6x times ln e. And ln e, a lot of times, you know, if e here was 7, I might take ln of both sides and I'd have ln 7 here. And then I'd have to divide away ln 7 on both sides. But ln of e is the exponent that turns e into e. That is 1. So now I have ln 31 equals 6x. And here would be a really common mistake at this point. You're so close to the solution, it'd be a shame to miss this one by dividing by 6 and doing this sort of thing, saying x equals ln 31 on 6. That is not correct. It should be x equals ln 31 on 6. And is ln 31 okay? Yeah, that's a good number. This is our solution. So third type, we have an exponential or an exponent that is a variable. We want to isolate that exponential term, take log of both sides, and solve for x. In this case, I needed to divide away 6. In theory, I needed to divide away ln e, but of course ln e is 1 to get my x alone. So there you have it. There's 3 different types of problems, 3 different processes for those, and that's what you're going to see with solving equations with logarithms in this course. Clearly, at this point would be a good time to practice some of those, only seeing one example of each. But I think the first thing you need to do is identify what type of problem am I dealing with. Some logarithmic terms where we group our logarithms, smash, definition, log. All logarithmic terms where we smash them on both sides and just drop the logs. Or a variable in the exponent where we isolate the exponential term, take the log on both sides so we can pull the exponent out as a coefficient in front of a logarithm. So there you have it. Practice up and stay tuned.